And as much as I'd love to tell you that we scientists come up with like silver bullet answers, like the bullseye on a target, that's not how we search for life.
So for example, we talk about early life on Earth. There are these zircon crystals where they look at carbon isotope ratios.
Yeah, totally.
So let's talk about signs of life.
Let's do it.
When I talk about what's different about Earth's life is that it's bathed in sunlight, what I'm getting at there without saying it is that most of the oceans are under miles of ice, miles of rock, or a super thick atmosphere, whereas we have this little tiny thin atmosphere, right?
Completely.
So if I wanted to look for signs of life, you can do it both remotely and you can do it, from a distance, right? And you can do it by sending a probe there, right? And aside from finding critters crawling around or skeletons, what are the different ways that you could potentially tease out that there is microbial life? Because I'm guessing that is the standard. If life exists 9 times out of 10, just like on Earth, if you visit Earth throughout its history, most of the time you're only going to find microbes. How do you go about, what are the different indicators that you could possibly that you guys have thought of so far?
So a bunch of scientists like myself, we study life on Earth through I'm going to call them different lenses. So some of my colleagues think a lot about DNA and genomics. And of course, if you find a molecule like DNA, and if you can be sure you didn't drag it to Mars with you, it's pretty cool. Right? So that's because that's like information in a molecule.
So finding a molecule, a life molecule. That is unquestionably a life molecule.
And let me give you a kind of little bit more there. Some of my colleagues are asking, like, how small does a molecule be before you're sure it's not life? Or another way of putting it is like, if I find, let me take acetic acid, which is vinegar. If I find vinegar molecules on Mars, that doesn't mean anything. Because you got all these like little organics floating around in space. But what if you find 10 things strung together? Can that happen without life? What if it's 20 or 100? So what I'm getting at here is there's something about the complexity that can give us a hint as to whether or not this was produced by a living thing. Your DNA is like millions of little bases strung together. That's cool. That's a lot of complexity. So if we found something that's 1 million bases long, like, come on, like that's pretty clear. So that's one lens. People like myself, we think a lot about energetics, as you kind of gathered from me talking, right? One way I define life is like it's got to keep itself at disequilibrium from the environment. And if I had those Star Trek tricorders, I could walk around and poke at things and be like, oh, look, that's the right mix of different elements all wrapped up in a little bubble that it may have been alive at some point. But the challenge with that, what makes it hard, is if I kill you, and I don't mean to be creepy here, but like let me back up, because this is a bad thing to do on your show.
in 2025.
I know.
In 1975, perfectly fine.
Can we edit that out? No. So if something dies and we bury it, it goes to equilibrium over time, and we can no longer tell it's there. Right? So you take it, if you take a piece of cheese and bury it in your backyard, and over a century you go back, like, you can't tell that a piece of cheese was there. Those chemicals diffuse, they get washed away, and all that stuff. You see where I'm going with this?
I see where you're going.
So when we go and look for life on Mars, and if it's 2 billion years old, we're not going to find an intact cell with all those elements in there. So my disequilibrium model is tough. So is looking for DNA. So the way we approach this is we take all of these 5 or 6 or 10 different ways, and we try to overlap them. If I got a little bit of evidence that leans in the right direction and someone else has a little bit, you can imagine starting to say, okay, this is more consistent. We got 5, 6, 7, 10 lines.
It becomes more than a coincidence when you have all these
things. That's it. Because right now we got 2 minerals. That's where we're at.
2 minerals.
It's a good sign.
That's not your millions of things strung together. Oh my goodness. So what would conclusive life look like then at the microbial level? If we were going to Enceladus and flying through the plumes and we took samples, right? What would it... I mean, that might be a weird question, because there's a point where you actually have living critters. That's clearly conclusive, right? But non-living.
Well, let me. So what I'm going to say is a bit half-baked again. But check this out. Like, if you look at Earth, you have all this oxygen gas in the atmosphere, And just like you alluded to earlier, oxygen is an element, as in O, the element O. Like that's all over the place.
Right.
But it's that O2 gas that's kind of an interesting fingerprint because it's like microbes did that.
Yes.
Right? And then there's this, there are all these different kinds of isotopes. And just as a reminder to those listening in, that's like when you have something like carbon, you got three different flavors of it, right? There's like a carbon 12 and a 13 and 14, and that has to do with the number of these things called neutrons, as we know, sort of stuck to it, right? So sometimes living things discriminate against one or the other, and they actually leave us what we're going to call it an isotope fingerprint. So when I look at methane on Earth, to give you a clear example, and I work with a very large mass spectrometer in my lab, for example, I can tell methane made by microbes versus methane made by volcanoes.
Oh, really? Because Mars is making methane. There's methane on Mars. Yeah.
But in order for us to tell if that methane came from, in order for us to get closer to figuring out if it's living things or dead stuff, we need to look at the isotopes. And that's hard to do.
You can't do that remotely. You got to need a sample.
So I'm not really sure if NASA has that tool. Maybe that's something you and I can look up after this. But I don't know that there are really high performance isotope analyzers like on Perseverance. I don't think that's the case.
How do you? Is it just by the mass? It just weighs more?
Yeah, it's a mass. Yeah, so you have to. That's what mass specs are good at. Yeah. And so that's the brilliance of sample return. Like we got to get samples back from Mars. Yeah. I would love to see us do this internationally and really put all of humanity's ingenuity to looking into what is the evidence in this rock, right? But we have to bring them home. I don't think we can do it on Perseverance. Yeah.
If there was life on Mars, what does that tell us about Mars?
I think broadly speaking, it tells us that there may have been a time in the past where Mars had maybe been in a position where we had liquid water, and it's looking like there probably was liquid water on Mars. And if that's the case, and I don't know enough about the core of Mars, but if there's any heat coming out from Mars in the past or now, if you have that temperature gradient, which you mentioned, that's cool, Hakeem. Because now if you got liquid water and you got some heat, it's not like the elemental composition of Mars is that different than Earth. I mean, it's not exactly the same, but I wouldn't be surprised. I wouldn't be surprised if we found microbes. I just wouldn't be.
It seems like we keep getting teased with these, there was the Martian meteorite with the microbes in it. There's the methane on Mars. There's water. Look at, there's still, remember the crater where you can see the seasonal changes. Then there's the water under the polar ice. All these little teasers.
Yeah, they're teasers.
Yeah, when are we going to get I want a catfish from Mars. Like, when are we going to get to the real life?
You might be waiting a while.
Real smoking gun.
So it's going to be a while for that catfish, Hakeem. But I'll say, look, I think that here's a question for frankly all of us, all of humankind. We a lot of us want to know this answer, right? A lot of people do. And if we do, we should be asking ourselves, what is a better way to get more conclusive evidence? And so I'm a big fan of this sample return idea. Because so many of the tools we have on Earth, we can't put on spacecraft cheaply or easily or practically, right? But if we can get a sample back, that changes things. And again, this just is something that I think is in the heritage of all of humankind. We should look at this together and figure it out. To me, if we get, and if I could wave a magic wand, what I would love to do, you're talking about probes, I'd send out probes to 6 best candidate places on Mars, or maybe 10. Just grab a sample. I want to look at them. And then I'm not going to promise everyone we're going to find life or not, but I'll bet you if we came back with 6 or 10 samples, we would have a much better idea if there was life, and we'd have a much better idea if there wasn't, we can walk away from it.
How about this? Instead of sending rovers, what about we send a team of geologists to 6 sites on Mars? 3 geologists.
That's it. That's a. So I think this is a cool idea. I also, part of me is like, can we do this with robots? This question came up during Apollo, right? Like, do we send people or do we send robots? Right? Because at the time when they were thinking about sending humans to the moon, this debate was raging. But I think, Hakeem, people were like, sending people to the moon is more than just grabbing rocks, isn't it? And so sending people to Mars, I get it, right? So if you really just want some samples, send some robots. But you're talking about something that I think is bigger. And it's an important question.